So today we're going to take our graphs one step further, and we're going to relate graphs to real-world events. We're going to sketch, we're going to interpret, and we're going to evaluate what are called story graphs. We're going to start with things kind of basic, and then we'll kick it up by putting numbers in. But we're going to start just by looking at some basic examples. So if we take a look at this graph, we're going to try to tell a story that goes with this red line graph. Very important is the title. The story we're going to tell really can change based on what's happening up here. And as you see, the title here is a trip to a friend's house. The next thing that's really important is to look at our labels. And we're going to notice here that our X label is time in hours. So as this red graph moves to the right, time is passing. Now, as the graph goes up, our distance from home is increasing, is changing in miles. So basically what I notice is there are three pieces to this graph, and I need to tell a story that describes what's happening. So this first piece is going up, which tells me that as time goes by, my distance is increasing from home. So my story could be that I start to walk to my friend's house. The second piece, notice that it flatlines, it goes horizontal, and that means that my distance from home is no longer changing here. So I would think that I've gotten to my friend's house, and now maybe we're watching a movie, playing some video games, shooting some hoops on the driveway, we're doing something at my friend's house. The last piece takes my distance from home and decreases it, which shows that I'm returning to home. So, something about returning to home, but before I tell the story, I notice that 1 and 3 have a very different steepness to them. 1, it takes a lot more time to go the same distance than 3 does. So somehow I'm getting home faster. So maybe mom took me home in a car. Now that's not the only story I could tell. I could have had myself biking to my friend's house, hanging out with my friend, and having dad pick me up by throwing the bike in the back of the, truck. Or I could say that I was walking to my friend's house like I did the first time. We did our stuff, and then I ran home because I was late. But either way, I have to take into account that the speed in 1 and 3 has to be different because of the steepness. Oh, by the way, called slope. So here is a totally different story, and we're going to sketch a graph to show the distance from home during a typical school day. So here, let's say, is somebody's graph. Notice the title is distance from home on a typical school day. We still have time in hours. We still have distance from home in miles. So we're going to start the time at 0, and we're going to talk about what does this story say about a student's particular trip to school. So let's just say that we begin the trip in the car. So here we are driving. Now notice that this piece flatlines. What might be a reason for that? How about, wrong one. How about we stop to pick up a friend? Now we continue the trip in the car, and you're going to notice that the steepness sort of remains the same. So it's the same mode of transportation, same types of, roads or whatever, speeds. So now, what is this long, flat part of the day that goes on forever? That's our time at school. Now, you might say, hey, wait a minute, Mrs. Ritter, I move around in the building during the day. And you would be right, but in terms of sort of perspective here, it's not that different compared to your trip from home. So that's why it's not going up and down here while you're at school. Although from my room to the media center feels like it's about 4 miles. Okay, now notice where our distance from home is now decreasing. This piece is going down. So what might be happening there? Well, we know we're going back towards home, but why is the steepness changed? Why is it taking longer? Well, one example in the story could be that you start walking home. And notice that I stop sort of at that same distance. So maybe I'm stopping at that same friend's house that I picked up on the way. Now, this last piece, what do you think about that? It's much steeper. So once again, have we been picked up by somebody to go home in the car. So that's what I mean by telling a story to go along with the graph. So this last one, some things have changed. The title is The Last Run of the Day. I see that we've got a skier over here. We're going to describe the parts of a graph of a skier's speed on a run. Down here is the time in minutes, and here you can see speed, miles per hour. This is no longer distance, it's how fast we're going. So as we go up in the y direction, our speed is going up. As we go down, our speed is decreasing, and a flat piece actually means we have constant speed. If it's on the x-axis, then it would mean we have stopped. But a flat piece means up here we're still moving. So I'm going to kind of go through this one with you in case you're not a skier. But does anybody know what this kind of slow, steady speed might mean for the run of a skier? For those out there, skiers, snowboarders, it could be that you're on the ski lift and you just go at that constant speed going up to the top of the mountain. Now you're going to notice this piece right here, our speed increases. So for those of you that don't know, but when you get off the lift, there is a hill to go down to get you away from the lift in case somebody crashes getting off the lift. Happens all the time. And notice I speed up, but then I'm kind of going at a constant speed, right? Constant speed coming off of that hill. And then all of a sudden my speed increases as I go over the hill, over the lip, kind of the edge of the hill, and head down the slope. Now you might say, how am I going at a constant speed? Well, unless you're barreling straight down, people will usually kind of do a slalom that kind of basically keeps them going at a relatively constant speed. Now all of a sudden, look at my speed drastically increasing here. Whoops, sorry, I forgot to put that. So I'm going along, happy as a very happy skier, and all of a sudden I just start picking up speed. So at this point in time, I'm kind of barreling down the hill, and all of a sudden, what's this drastic piece? Yes, I'm out of control in a rapid deceleration and crash in a tree. Anyway, that gives you an idea how different the story is when it is speed. Now what we're going to do is start putting numbers in, and I'm going to do this air track, and then we are going to do another one at the Pocono Speedway. And then I'm going to go back to kind of connecting those ideas of distance and speed. Okay, so first of all, an air track, there are basically these little sleds, and we're going to just have one on there. This picture has two. And there is a device here that will blow out air, like a burst of air. So notice that the sled is sort of starting in the middle of the track. And the air is going to blow. And if it gets to the end and it comes with the right speed, it will bounce off and come back. There's kind of like a bumper, and it would return. So what we're going to do here is we're going to notice this is the track position. So this is where the sled started. And you're going to notice it's starting kind of in the middle of the track. And it's going to move towards one end. And then it's actually going to go back to the other end. And let's, tell the story of what's going on here, okay? So the track, we burst a little, burst of air, and it doesn't go very far, and it stops. So here it's just sitting still, and we realize, oh, we should have forced more air out. So we send more air out, and we send so much out that it hits the bumper, it comes back and hits the bumper, and then stops kind of where it started. Kind of like the idea if you've ever played pool, and you kind of hit a ball just kind of a little bit, and it doesn't even go to the edge, and then you just really hit it hard, and it hits and goes to the other side and hits again. That's kind of what's happened here. All right, so let's go back to our discussion of domain and range. When we look at a graph to determine domain, you're looking at the x values. So we're looking at where did the sled start for time and where did it end for time. And we notice it goes from 0 to 10. So we're going to write that as an inequality. And I'm going to be honest, whether you put the equals or if you put strictly less than, I really kind of accept it both ways at this point in time, because the question really is this point of inflection, is this point of going from moving to stopping, is that still increasing or is that constant? And we really could kind of argue about that. So that's why whether you put the equals in there or not, I go for it. All right, so if you have this, you'll have a different interval notation, if you don't have the equals. So what would your interval notation be? Let's see if you can do that. So this is where interval notation really is handy, and you should have had brackets. And again, if you didn't put the equals and you put parentheses, I'd still give you 100 on this one. Okay, so the next, what is the range of the sled? Now you need to turn your thinking and ask, what's the minimum y that comes out and what's the maximum y that comes out? So the minimum y is right here, and it's -8. And the maximum y is up here, and it's 5. So what would the range be in terms of an inequality? So your minimum is -8, your maximum is 5, and once again, equals inclusive or not, we could argue both ways. So our interval notation for that? Okay, so now let's talk about increasing and decreasing. So imagine you're riding this curve going left to right. As you go left to right, notice here, this piece is going up. That's called increasing. Here, it's flatline. That would be constant. And here it's going up. That's increasing. And then notice a drastic drop off. We're going down. That's decreasing. And then this piece is increasing again. Now let's look at this language. On what domain interval is the function decreasing? Let's first find the piece that's decreasing. It's from here to here. And it asked on what interval of the domain. So for what x values is it decreasing? So x, see, it starts at 5 seconds, and it's decreasing, and when does it stop decreasing? At 8 seconds. So between 5 seconds and 8 seconds, the track position is decreasing. And once again, interval notation. Now, what domain interval is the function constant? I'd like you to try this one yourself. This is the constant piece, and it's happening from 2 seconds on the domain to 4 seconds on the domain. And then again, interval notation. So that's just starting to put some numbers in and understanding the terms increasing and decreasing. So let's head off to the racetrack. So this is Poconos Raceway, and this is a picture of the course. This is the Indy car right here that's going to ride, and this is the start line, and he's going to go driving here. Now, when you're driving, you have to slow down as you go into a corner, and you'll accelerate, you'll speed up as you come out. That's the back stretch. Then we're going to slow down as we go into turn 2, and we're going to speed up coming out of the turn. And then finally, we're going to slow down into turn 3 and then speed up. And that would be considered a lap. They go around a lot more than that, okay? Notice that the 6-degree turn is the tightest turn. So we're probably going to have to slow down the most going around this turn. So basically what I've done is graphed the car for 1 lap. So see turn 1, turn 2, turn 3. Along the x-axis is the feet, how far you're traveling. And your y this time is speed. So from here to here, from the start to turn 1, is kind of from here to here on the racetrack. And right here would be turn 1. So that's when you're coming around the track, okay? So let's take a look at this. So notice the x is going to be how far you've traveled from the start. So 1,000 feet would be right here, and then we're going to be taking that turn until we get to 1,400 feet, and then we're going to be on the back stretch, okay? The x is where you are positioned on the track, a little bit different this time. The y is how fast you're going. Look at that, 235 miles per hour on that start stretch. Now notice we slow down to 120 to take that turn, start speeding up again, and then when we hit the back stretch, we're back up to that 235 miles per hour. Okay, so just to give an idea there, let's answer some questions about this graph. I got the graph up here. I apologize that the little thing about feet here got taken off, the label from the last slide. Okay, what is the car doing between 1,400 and 3,000 feet? Now remember, feet is your x. Do you see it right there? Between 1,400 1,400 and 3,000 feet. What is the car doing? Did you think? Accelerating, it's speeding up, right? What is the minimum speed during this entire lap? Remember, this is the graph of one lap. And where does it occur? For minimum speed, you should have been looking at the y coordinates. Did you get the 110? And where is that happening? It is happening down in that turn 3. It's happening 7,000 feet into the race. Where is the longest interval of increasing speed, and how much does the speed increase during this interval? Did you see that from 7,000 to 8,700, that 1,700 feet is the longest sort of increase of speed, and it changes from 110 miles per hour to 235. 235 minus 110, it's an increase of 125 miles per hour. But that is the longest amount of the track that you are speeding up. Where is the shortest interval of decreasing speed, and over how many feet does this occur? So now we're looking for decreasing, and there's 3 places that happens. Where is the shortest, and how many feet does that happen? Oops, sorry. I went and hit the wrong thing here. Let me get back on. There we go. So it's right here, right? This very rapid, between 1,000 and 1,400, 400 feet. That is the kind of the shortest amount of track that we decrease in. What is the y-intercept? So where does this graph hit the y-axis, right? You can see it right there. And what does this mean? So it happens at 235. So at the start, that's 235. What's going on? Well, in case you've never watched racing, you're actually moving when you hit the start line. So they position the cars based on qualifying, and you actually hit the start line already going 235 miles per hour. Okay, let's do one more graph here, and then I'll just do a final tying speed to distance one more time. So this is Biff's morning jog. So again, we're back to distance from home, in yards this time, and this is time. What is Biff's maximum distance from home, and when does this occur? His maximum distance from home, go ahead. Did you put that it's at 500 yards, and it happens 3 minutes into his jog? Where and for how long did Biff stop jogging? He stopped jogging at 300 yards from home, and he did it for 2 minutes. From 4 minutes to 6 minutes, he stopped. For 2 minutes, he stopped. So he's jogging, and for some reason, he turned around and started to head back for home, and he's literally stopped here, and then he goes back, okay? What are the x-intercepts? Where does this graph touch the x-axis, and what do they mean? Well, those 2 points, the x-intercepts are 0 and 9, at 0, 0, and 9, 0. And those are the times he's at home. So Biff's whole jog only lasted 9 minutes. My guess is he started jogging and realized he left something home, maybe his phone, maybe his earplugs or something, his headphones, whatever, and he went back to get them, kind of stopping on the way. Maybe he stopped to check his pockets to see if he had stuff. But that's just another example of a story graph. All right, so before we go, I want to take that same graph that was a distance graph and show you its coordinating speed graph. So I'm going to take that off and kind of show you what's going on here. So these are actually the same graph for Biff's morning jog. But this one is speed, and this one is his distance from home. So remember that a straight line on a distance graph, so this straight line, no matter where it is, always means that he's going a constant speed. If it is a horizontal flat on a distance graph, it means 0 speed. So here he's speeding up. Right here, this is a constant speed. So he starts running, And he has gone 100 yards in 1 minute. So over this right here interval, right here, his speed is 100 yards per minute. And then in this little turn, he's speeding up again and then hits a constant speed. Now notice this time he went from 100 yards to 500. He went 400 yards, and how long did it take him? 2 minutes. So 400 yards divided by 2, he's going 200 yards per minute. And there's his speed that corresponds. Now wait a minute though, why is it going all the way up to 400? Because even though he turned around and went to go back home, this piece is still going 200 yards in 1 minute. So he's going that same speed. Even though he turned around and went home, he kind of just turned quickly and went right back to that speed. For this part right here, notice he is not changing his distance from home, and that's why we see the rapid slow down, and in between that time, he's not moving. His speed is 0. Now he's still heading towards home, but notice he covers from 300 to 100, 200 yards in 1 minute. Once again, 200 yards per minute is his speed for that little piece. And then the last 2 minutes, he's only covering 100 yards. 100 divided by 2, that's why he's going 50 yards per minute, and then he comes to a stop. So whether he is going away from home or towards home, his speed doesn't become negative. So why isn't it negative? Well, first of all, speed is what's called a scalar number. It doesn't have a direction to it. If you change the word to velocity, which you will do in physics in high school, that is called a vector quantity. Oh, by the way, this is the vector dude from Despicable Me. And that will have a direction component and talk about not only the magnitude or what number, like 50 miles per hour, but it'll also talk about in what direction. So we're not going to do that right now. So all of our speed, 45 miles per hour, 40 feet per second, will always be a positive. So even though he turned around and went home, his speed is still going to be a positive value, excuse me. So once again, just to make those connections, this is your distance. If it is a flat horizontal piece on a distance graph, your speed is 0. If it is a line, right, that would be a constant speed. He went 10 feet in 1 minute. And so on the speed graph, you'd see that in that 1 minute, you're at 10 feet per second. If you have kind of a curve, let's see that, that means that your speed is gradually changing. So you'll notice here, I'm running at a constant speed and I start to slow down till I get here and stop, okay? So that's kind of what's happening, you'll notice. So I'm going at a constant speed and I slow down until I stop. So a flat horizontal piece on a distance graph means you're not moving. A flat horizontal piece on a speed graph, if it's at 0, means you're not moving. But if it's up here, you're moving at a steady speed. These on a speed graph means you're slowing down or speeding up. So just, you've got to understand the difference of those two when you tell your stories. So we have talked about speed graphs, we've talked about distance from home graphs. We'll do more when you come into class. We're just, really starting to pull all of these graphing ideas together and kind of connecting them to real world situations. Hopefully we got a chance to, the other day, do the Desmo with the little turtle, so you already had kind of an idea, but now it's time for you to practice. And so we're going to do some problems telling story graphs, and then we will tie this idea with like the Pocono Speedway to some other worksheets coming up in the future. So guys, I hope you have a great day.